Today we're going to take a look at simplifying radicals and then eventually radical operations. So first let's start with our definition. For any real numbers a and b, if a to the nth power is equal to b, then a is called the nth root of b. Now this is the notation for these radicals. So we're saying a is equal to the nth root of b. That's how we read this radical expression right here out loud. A equals the nth root of b. Okay, little vocab for you. This n right here, this is called the index of the radical. So if it's a 2, it's a square root. If it's a 3, it's a cube root, and so on. Okay. Then the symbol itself, that's the radical symbol. And the expression inside, in this case the b, that's called the radicand. Okay. All right. So a quick little example of this. If I had something like 5 to the third power, well, that number comes out to 125. So that means 5 is equal to the third root or the cube root of 125. Okay, so the exponent here, this exponent, becomes this index. All right. So let's take a look at these 4 problems and try to find each root. Now on A, we're looking for the square root. There is an implied 2 here. If there's no index written, it's automatically a 2. All right, so this is the square root of 64. Well, we know the square root of 64 is equal to 8, and that's because 8 squared is equal to 64. Okay, let's take the one next to it. Now I want to do the cube root of 64, which means something to the third power has to equal 64. Well, what number to the third power gives me 64? Well, that happens to be 4 to the third power. So this value is a 4. The cube root of 64 is 4. Okay. How about the fourth root of 81? Well, the fourth root of 81 means something to the fourth power is equal to 81. Well, 9 squared gives me 81, and 9 is 3 squared, so this is actually 3 to the fourth. 3 times 3 is 9, times another 3 is 27, times another 3 is 81. So this value comes out to a 3. Okay, one more. The fifth root of 32. So you guessed it, something to the fifth power is equal to 32. Any guesses? Okay, it's a 2. So the fifth root of 32 is a 2. Now, how am I figuring all of these out? Well, when we're simplifying radicals, we want to be able to take a look at perfect squares, perfect cubes, and so on, and we want to look for factors of that go into the radicand. Or sometimes maybe the radicand matches perfectly. So let's make a list of all of our perfect powers. So the perfect squares are 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. And we could go higher, but those are the numbers that we need to be very familiar with. All of these numbers are perfect squares, which means I can easily find their square roots. Then when it comes to cubes, well, 1 to the third is 1, 2 to the third is 8, 3 to the third is 27, 4 to the third is 64, 5 to the third is 125. And I could keep going, but these numbers are already getting pretty large, so they're not super likely that we're going to have numbers higher than that to deal with. All right? Then we've got the powers of 4. 1 to the fourth is 1, 2 to the fourth is 16, 3 to the fourth is 81, 4 to the fourth, triple-digit number, we're not going to go that high. Okay? And then powers of 5, 1 to the fifth is 1, 2 to the fifth is 32. And that's pretty much the only only two that we're ever going to use. However, 3 to the fifth, that comes out to 243. So you can say where we're not going to keep going. Now, these are numbers that we're going to use fairly often in order to try to simplify radicals, which we'll see a little bit later on in this lesson. Right? The next thing we need to take a look at is, well, how do we deal with variables? Right? All right. So when we look at variable expressions, we're still looking at the index, and we're trying to figure out what thing to the index power gives us the radicand on the inside. The only problem is sometimes we're going to need absolute value in our answer. That's going to happen only if the variable being pulled out has an odd exponent, but only if we had an even index to begin with. All right, we'll talk about the absolute value part in a moment. But first, let's take a look at problem A. So the way I think about this is something to the fourth power has to equal x to the eighth, y to the fourth. Okay, so this kind of goes back to that factoring with difference of squares or difference of cubes, figuring out that sort of setup. Something to the fourth power is x to the eighth, y to the fourth. So I need to do x squared, and then x squared to the fourth gives me 8, and then y to the first. So that means that this is equal to x squared y. Okay, but if I read the blurb at the top again, it says, if the index is even, remember this number is the index, which it is even in this case, then you might need absolute value in your answer. We're only going to need it around something that has an odd exponent result. So this right here, I need absolute value around the y, okay, because there was an odd exponent on that y. And that's just to guarantee that the answer comes out to a positive, because we have the positive fourth root of x to the eighth, y to the fourth. We don't have a negative out in front, so I can't have a negative answer. Okay, so that's why the absolute value becomes necessary. But again, we only need to worry about it with an even index, and only if we ended up with an odd exponent. Okay, let's take a look at B. On problem B, I've got to figure out, I'm going to go down a little bit further here so I have more space to think. Something to the third power has to equal a to the ninth, c to the 12th. Okay, remember, we're doing power to a power, so we're multiplying exponents. So I need a to the third. Those two threes will multiply, give me a 9. And then I've got c to the fourth. So this is equal to a to the third, c to the fourth. Okay. The question is, do I need absolute value in my answer? I have an odd exponent on a cubed, but right here, this is odd. So that means there's no absolute value needed. No absolute value needed because it had an odd index to begin with. So I don't need to worry about it. Okay? And that's because I can take an odd index root of a negative and it'll come out to a negative, so it's okay. I don't need to switch it back to a positive. All right, and then for C, you guessed it, something, the index is a 6 to the 6th power equals m18 v to the 6th. Okay, so I'm going to do m to the third because 3 times 6 gives me 18, v to the first because 1 times 6 gives me the 6. So this is equal to m cubed v, or v to the first. Now, this was an even index. So there's a possibility that I need absolute value. And in this case, I need absolute value on the whole thing because both variables had odd exponents. We'll talk more about the absolute value in class, but it's something that we'll kind of pull back in multiple times throughout the next few lessons.